So good morning, everyone. Welcome. It's 10:01, and I'm super excited to be back with all of you to talk about part two of double integrals across polar regions, or with polar coordinates. Um, I was kind of looking over my notes yesterday and realized that again, just how interesting it is to jump straight into a course um, after having such time off. The integrations are pretty straightforward. We're integrating complicated things like r to the fourth, but the setup, the working with the limits of integration, that's complicated. And of course, polar coordinates are new to most folks, or at least it's been a while since most of you folks have done them. So I just wanted to encourage you to keep plugging away at the polar coordinate stuff, to keep practicing. The class will kind of come fast and furious right here at the beginning, but mostly that's just to get everybody up and running. And then we'll start to hit our stride probably next week. If you find that you missed an assignment. So when last we saw our intrepid heroes, we were working through double integrals across polar coordinates, and I wanted to begin by working through another example. So this is example 3 in the notes, and the question is to set up an integral to represent the integral across the region R of just some arbitrary function g of r theta. And when we do this thing where we put in an arbitrary function, the point is that I don't care about having a number. What I'm really trying to focus in on is the process, and specifically the limits of integration. So at the end of the day, our answer is going to be an integral. It's not going to be a number. Our answer is going to be an integral, not a number. And in this case, so continuing on, so the integral across the region R of g of r theta dA, where r is outside of the circle r equals 2 and inside the equation r equals 4 cosine theta. And so our process is going to be the same in most of these questions, or some variant of each other. We're going to sketch the picture, we're going to find our limits, and then we're going to integrate. And we've been using this fancy technique for sketching pictures. This fancy technique is called graphing calculator, or Texan friend. And so I'm not going to spend a lot of time on sketching the picture, but I do want to spend a little bit of time on using the picture to find those intersection points and also finding the limits of integration. So I'm going to switch over to my doc cam. Okay, so here's the picture, and the question asked us to find the region outside the circle r equals 2. So here's r equals 2. And inside r equals 4 cosine theta, which if you work through it is also a circle. It's just centered at x equals 2, y equals 0. And so we want outside the left circle, inside the right one. So we're after this region here. Okay, that's great. And we're going to need to find where the two curves intersect. And so I want to just highlight those points and talk about the process for finding those two intersection points. So notice, in order to find the intersection points, that would be where the two functions have the same values. So the intersection would be where 2 is equal to 4 cosine theta. The 2, in this case, is giving me that 2, and the r equals 4 cosine theta is giving me the 4 cosine theta. We can divide both sides by 4, and we get 1/2 equals cosine theta. And this is one of those nice points on our unit circle. And so we get that theta is equal to pi over 3 plus 2k pi. Make sense? Any questions so far?
What's this k?
The k would be an integer. So this would be like, so k would be equal to like dot, 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 plus minus 2, plus minus 1, 0. So it could be, it's funny that I wrote it this direction. So it could be any positive or negative integer, including 0. So this would be 2k, 4k, 6k, 8k, or sorry, 2 pi, 4 pi, 6 pi, 8 pi, or it could be 0 pi, or negative 2 pi, negative 4 pi, negative 6 pi, et cetera, et cetera. Does that make sense?
Thanks.
No problem. All right, that's great. But this means that there's actually an infinite number of values that theta could be, and it's always a little bit difficult to integrate when you have an infinite number of options for your limits of integration. Like, well, which ones are they? So let's think about this for a second. So if our angles rotate around like this, what is going to be the theta when we first hit that blue spot based on the work that we just did?
Pi over 3.
Pi over 3. So this is going to be pi over 3. Okay. And then theta wraps all the way around, and it hits this point down here at, ooh, this is a little bit odd. What's going on? What's going on there? That's a little bit odd. So help me out. There's a little bit of a subtlety here. Can you guys see what's going on?
Isn't it just, is it 2k pi? It's because it is adding 180, I think it's adding 180 degree.
180 degrees. Because our unit circle will have x equals a half, and that will happen here and here. So this would be at pi over 3, and this one would be where?
5 pi over 3.
5 pi over 3, or also, this would be 5 pi over 3.
Negative pi over 3?
Or negative pi over 3. Good, good. So, exactly.
So it's k pi, right? Just k pi.
It's not k pi, because k pi would be pi over 3, and then the next point would be down here.
Oh, I got you.
So we actually have to list off both of these values. So you could do the pi over 3 plus 2k pi, and then we also have the 5 pi over 3 plus 2k pi. That makes sense? So the pi over 3 is up here, and then we're next getting hit it at pi over 3 plus 2k, 2 pi, pi over 3 plus 4 pi, etc. This one we'd hit at 5 pi over 3, 5 over 3 plus 2 pi, etc., etc., etc. Okay, so what are our limits of integration? So what's our lower, so we're gonna, our lower limit, what's our upper limit? There's a little bit of a subtlety here. So
The lower will be pi over 3.
So let's try it. So write in pencil, don't write in Sharpie. Just pro tip. So pi over 3. And then our upper limit?
5 pi over 3.
5 pi over 3. So let's see what happens. So what that's saying is...
It is, I think it is including the other circle, I think.
Yeah, you're onto something. So let's see what happens. So that would be saying we start here, we rotate around to pi over 3, and at this point we start tracking things. So now we start adding up area, add up area all the way around to 5 pi over 3 and stop adding up area. So that would be adding area all in this region here.
So it should be like the opposite, right? So that we go the other way.
So if we went 5 pi over 3 to pi over 3, then that would say start here and add up your area all the way around to there. So you're going to get the negative result, but you would still get the wrong part of the figure.
Could you please show that one more time, that last demonstration?
So Dusty, why don't you add just pi over 2 to 5 pi over 3, so you'll get the lower and upper?
We could. I'll show you in a second. Let me go back to Enrique's question. So if we went from 5 pi over 3 to pi over 3, it's saying start here and then work your way backward to pi over 3, which would be this direction. So again, we grabbed all of this region and we missed the orange region that we care about.
So you start from 5 pi over 3 and add just pi over 2.
If I started at 5 pi over 3
and add pi over 2, so you'll get the upper one.
You mean 2 pi over 3?
I think negative pi over 3 to pi over 3.
I think that I like Vu's approach. It's the cleanest, although what Jay was starting to say would have worked as well. So what we can do is we can use for our lower limit, we can use negative pi over 3. And for our upper limit, we can use pi over 3. So here's 0. So let's start at negative pi over 3 and work our way past 0 to pi over 3. That make sense? So here's 0, just by way of reference. Start at negative pi over 3 as your lower limit and work your way to pi over 3, which is your upper limit.
Question. Why can't we go that way if we write it as 5 pi over 3? Why do we have to go the other way?
If that was sort of what Jay was starting to say, if you wanted to start here at 5 pi over 3, then you'd have to go from 5 pi over 3 to 2 pi to 7 pi over 3. So your limits would be from 5 pi over 3 to 7 pi over 3. And that would work as well.
Oh, okay, gotcha. Thank you.
Yeah. So here's the pro tip.
I think you have a question.
Oh, question from Robert. Go ahead.
I was just curious, Dusty, why we don't just start by simplifying it through symmetry.
Symmetry is a beautiful thing, and I think that that's a great question and a good reason to use symmetry. I think the reason why I wanted to bring it out in this particular case is because I'm guessing when you hit your homework or you hit your assessment questions, everybody's going to run into some issues in this. And so if we don't tackle those subtleties anywhere along the line, then you'd sort of be ill prepared to handle them. But in the next question, I think we are going to use symmetry in a big way. So it's a good question.
Okay, thank you.
No sweat. So let me just show you how you could use your Texan friend to verify. So here I graphed both regions, and if I wanted to verify that this was right, I could change my window to go from negative pi over 3 to pi over 3. You may need a smaller step size. We'll see that in a second. And then just graph, and sure enough, you get the nice partial moon that we wanted to see. And so it gives you, the graphing calculator gives you a way of checking to see whether your limits of integration make sense. It's not perfect, but yeah, but it's a pretty free way of checking things, especially if you're not under time constraints. Questions? Ready to move on?
So Dusty, so 1/2 equals to cosine theta. So cosine is even, so it's just like negative pi over 3 and pi over 3. It's just directly we can get the answer.
Yep. Exactly. Okay, so we sketched our picture. We found our limits of integration. We can set up the integral, and so our integral. Am I sharing my screen? Sorry, I'm looking at it and forgot to share the screen. There. So we're going to set up an integral. So our integral is going to be the integral over the region of g of r comma theta dA. And then, again, we'll replace the dA with an r dr d theta. And our limits of integration are going to have r's that go from the inside limit. So that would be starting at the origin, working its way out. The inside limit comes when you hit the circle r equals 2. The outer limit is going to be when we hit the outside circle, which would be 4 cosine theta. And the smallest theta, as we just spent a long time talking about, is minus pi over 3, and the upper limit is pi over 3. Let me show this in the manipulate. So in the manipulate here, we've found our region from negative pi over 3 to pi over 3. And notice we start at the origin. We don't grab anything until we hit the red curve at 2. So that's going to be our lower limit of integration. And then we grab everything all the way up to the outer limit, which would be the 4 cosine theta. And you can see, sometimes it's hard to visualize, but at negative pi over 3 is that exact intersection point. And so as long as we're between negative pi over 3 and 3, we're only grabbing the stuff that's inside this region, but outside the red circle. Questions? We're ready to go on.
I hope this question doesn't take up too much time, but if, let's say, our first circle wasn't centered at the origin, that would just affect the integral, our lower limit of our dr integral?
The way so the question was, what if this circle had been maybe shifted to the left or something like that? And so yes, indeed, it should just impact our lower limit, although probably the intersection points would be different as well.
Oh, yeah. Right. Yes.
Cool.
Thank you.
Let me just, before we go on, let me stick you into a breakout room just for a minute or so and see whether there's questions that you have for each other or things that we're missing that we need to talk about before we go and do a more complicated example. Any questions, trig comments, process questions? Waiting for the last few people to join us again.
So next, are we actually going to find the equation to integrate with, or?
In our next example, we're going to start a new question from scratch, so we're not going to worry about that particular question any longer. In general, yes, once we find our limits of integration, then we would go ahead and find the antiderivative. But frankly, the integrations are in some ways the easiest parts of this class once you actually get everything set up. Wolfram Alpha is really good at integrating. It's not very good at setting up limits of integration, for example. So did that answer the question?
Yeah, I mean, so I'm looking at it and I understand like the limits. I'm just a little confused what the actual equation we're going to be integrating with.
Got it. So why don't you hang on to that question? I think that I think you'll see it. Basically, we didn't do step 3. We just set it up and then left the question there. In the next question, we're going to actually work our way all the way to a number at the back end, and so I think you'll feel a little bit more peace with the world.
All right, thank you.
You're welcome. So welcome back, everyone. Let's look at another example. So as we saw in Calc 3, double integrals can be used to find the area of a region. So when you do that, you want to have the integrand of 1. So if we say find an area, then you know that means you want your integrand to be 1. dA, if you ever see a double integral with a 1 dA, then you know we're looking for an area. So kind of you can look at it either way. So in example 4, we're going to use a double integral to find the area enclosed by the 3 petal rows r equals sine 3 theta. And do I have a typo here in petaled? I think I do. Anyway, moving on. So our first step is to sketch the graph. And so here's your 3 petal rows. And so notice if you watched it sketch out, it would swing from the origin out, around. It has the kind of this nice loopy feel to it. And now I want to take advantage of the symmetry that Robert was calling me out on in the last example. And so we notice that this 3 petal rows, area is equivalent to 6 times just half of a single petal. And so we're going to focus in on trying to find the area of this little half petal and kind of work from there. So let's see if we can find those limits of integration. So here's our picture. And so we know that our limits are we got to find 2 sets of limits. So one is at the origin where r equals 0. And so our function that we're given is sine of 3 theta. We want to know when this is equal to 0. And so we know that sine itself would be 0 at 0 and pi and 2 pi and 3 pi, et cetera, et cetera. So this tells us that 3 theta is equal to, we call it 0 plus k pi, or theta equals pi over 3 times k, or k times pi over 3. What's the k value the very first, first time, so to speak, that we hit the origin?
0.
0, right? So when k equals 0, theta would be 0. We probably knew that one already. So that would be when r equals 0. How about up here at the other point? What's our r there?
1.
So r equals 1. So we have sine 3 theta equals 1, which would tell us that 3 theta would equal, what, pi over 2 plus 2k pi, or theta is equal to pi over 6 plus 2/3 k pi. Does that, my trig seems solid? Okay. So what's going to be the theta here at the base?
0.
And the theta at the top?
Pi over 6.
Pi over 6. We could, again, test this Texan style if we were so inclined, but maybe we won't. Okay, so we found our limits of integration, and we can use this to set up the integral. Notice I have this little caution, and the caution is you just have to be really careful when you're setting up the limits of integration with things that are trig. Because of the periodicity, strange things can happen. And so an extra double checking on your calculator. It's just flat out is a good idea to make sure that you don't miss something, because we can represent points in so many different ways, and so that just makes for some added excitement that you don't have under rectangular coordinates. How about that? So we have our picture, we have our limits of integration. The last step is to set up and evaluate the integral. So remember, since we're trying to find an integral to represent area, our integrand is 1, but our dA, since we're in polar coordinates, is being replaced by the r or dr or d theta. Again, you could do it with d theta on the inside, but most of the time our brains just don't work that well, and so I would encourage you to, at least by default, put the r's on the inside. So our r's are running from the inside of the curve, from the origin out to the edge of the petal. So from r equals 0 to r equals sine 3 pi, r equals 0 to r equals sine 3 pi, and our thetas are running from 0 to pi over 6. So this will give us the area of a half petal. We're multiplying by 6 because there were 6 half petals in our 3 petal rows. I think the only other, most of the rest of this is pretty straightforward. The only other part that's worth really commenting on is here you've got your sine squared. And so anytime you're trying to integrate a sine squared, you're going to have to use that half angle identity. And so remember that the angle in the square is doubled in the half angle identity. So here it's sine squared of 3 theta, cosine of 2 times 3 theta, or 6 theta. Questions about this? And Croy, did that give you a little bit more peace because we've actually worked through the integral all the way to a number?
Yeah, yes, it did.
Quick question.
Go ahead.
So when you're putting the limits back into the integral, you don't really care about the constants with a k? Like
Correct.
this.
Correct. The k's are there for mathematical completion, or consistency, because I'm trying to solve an equation. But if I'm actually going to integrate, I need one number. I don't need an infinite number of numbers here. Correct.
Makes sense.
Yeah. So the mathematician in me has to put those in there, but the engineer doesn't need to, if that distinction makes sense. Like the engineer is just like, I need a number out the other end, and so it'd be good to go.
Well answered.
Do you want me to go into breakout groups or just keep going? Let me know where you're at. Give me a thumbs up if you're happy and we should just keep going. Nice. And you can do that using the participant or the thumb. Nice. Nice, nice. Okay. Let's move onwards and upwards. So there's a little historical anecdote before the next question. So famous story about a 19th century Scottish physicist, Lord Kelvin. So this is the guy that this guy was so cool, he got his own temperature scale all the way down to absolute 0, right? This is Lord Kelvin. And Lord Kelvin walks into his math class one day and he asks his class, he says, and he writes down this expression on the board. He says, a mathematician is somebody for whom this statement right here, that the integral from negative infinity to infinity of e to the negative x squared dx equals root pi. It's like a mathematician is someone to whom that is as obvious as 2 times 2 equals 4 is to you. He's like, all right, calculus 4, you think you're mathematicians? Well, is this as obvious as 2 times 2 equals 4? And so I think we should spend a little bit of time talking about this particular expression or equation and also talk about just how obvious this really is and its uses. So kind of funny story about Lord Kelvin, and let's do some math to figure out what this is all about. This one is worth working out by hand, and there's definitely some subtlety here. Oh my gosh, integral from negative infinity to infinity of e to the negative x squared dx. Let's start by drawing a picture because maybe you don't know what this thing looks like. So here is y equals e to the negative x squared. And it does approach the x-axis, so it should be 1. So what does this curve look like?
That's symmetric towards the y-axis.
Yeah, it's symmetric around the y-axis. This is the famous, this is the bell curve. That's why we care about this thing. That's why we're going to spend some time on it. And the fact that it has a good story. So this is the bell curve. This is what it looks like. And we're asking ourselves, what's the total area underneath this curve? And Kelvin says, well, it's obvious. The area under this thing is, any kindergartner can see that area is square root of pi. So we're all feeling pretty good about ourselves. So one thing we could notice right off the bat is that there's symmetry in this picture, right? So rather than going from negative infinity to infinity, let's just double the integral from 0 to infinity of e to the negative x squared dx. Okay. All right, now we got to be a little bit clever, and we got to be a lot of bit clever. So what we're going to do is we're going to square both sides of this equation. Why? Because, well, it's obvious, right? Because we're just being clever. We're having fun. We're doing math. So I squared is going to be equal to 4 times the integral from 0 to infinity of e to the negative x squared dx quantity squared. Why are we doing this? We're doing it because we can, and because it's going to end up working out for us. Not because it's not obvious. Certainly to me, when I first saw this, it is not obvious why we would start squaring things, but it ends up working out. Questions before we continue?
So are we going to treat this like a polar equation?
Polar is going to show up in a couple minutes. Yeah, so there is a connection. Hang with me. Okay, let's divide both sides by 4 and write out our square old school style. So what does it mean to square things? That would mean integral from 0 to infinity of e to the negative x squared dx times integral 0 to infinity e to the negative x squared dx. What kind of critter is this integral? Does this definite integral represent? Is this a vector? Is it a matrix? Is it a function? Is it a family of functions? Like, if assuming it exists, when we work through all this kind of thing, what does all this stuff represent at the end of the day?
A scalar?
A scalar, exactly. It's a number. Scalar, right? It's a number or a scalar. Is the x important to this number? Are there going to be any x's in that number? No, right? The x is just sort of a dummy variable that lets us get through the question. So since the x is just sort of an arbitrary choice, we're going to take advantage of that. And we're going to rewrite this as the integral from 0 to infinity of e to the negative x squared dx times the integral from 0 to infinity of e to the negative y squared dy. So notice the second integral went from x's to y's. You say, well, how can you do that? Well, the letter doesn't matter. The letter is somewhat arbitrary because it's a definite integral. So we could pick whatever letter we wanted. My name's Dusty, so I could have chosen D for it, except for then you'd end up with DD, which is confusing. And at this stage, I want to take advantage of a theorem that I named, that's from last quarter, that I decided is important enough that it needs a name. So this is the theorem that I call handy trick. So handy trick says that if you have a double integral of a product of two different functions, where the blue one is a function just of x, and the orange one is a function just of y, that you can split up that double integral into the product of two single integrals. And this is assuming that your bounds are numbers. So this wouldn't work. So if you had the double integral of sine xy dy, or sorry, dA, this would fail because this is not g of x times h of y. But it would work if you had sine x times cosine y dA. So here it's not handy, and here it is handy. Okay, so this is a theorem that you would have had from last quarter, but it basically lets us take apart double integrals and write them as two single integrals, or in this case, it lets us take these two single integrals. This one's just got x's in it, this one's just got y's in it, and it lets us write them as a, single double integral. So this is going to be equal to the double integral from 0 to infinity of e to the negative x squared times e to the negative y squared dx dy. Questions before we start changing coordinate systems on you?
It seems like x squared plus y squared going to be r squared.
It sure does. So this is e to the negative x squared plus y squared. And we're thinking to ourselves, every day is a holiday, right? Because this is going to be an e to the negative r squared. What's your dA, dx, dy going to be replaced by?
dA?
R dr d theta.
So this is going to become r dr d theta. Good. And then we need to deal with our limits of integration. So let's just think about those limits of integration for a second. So our region is x is from 0 to infinity. So that would be all this stuff. Y is from 0 to infinity. So it would be everything in the first quadrant. So if it's everything in the first quadrant, where do you want your r's to range? Where do you want your thetas to range?
So theta will be from 0 to pi over 2. And r is, I think, infinity. Infinity.
It'd be 0 to infinity.
0 to infinity, yeah. 0 to
Exactly.
infinity.
Exactly. Craziness. Okay, antiderivative of this stuff. think it's negative 1/2 e to the negative r squared from 0 to infinity d theta. Oh, somebody's muted. Okay. And back in Calc 2, you made a big deal about these improper integrals with the limits of infinity. And we said you had to write limits and all that kind of stuff. We're going to be a little bit more fast and loose here because you paid your time, paid your dues. And so if I put in infinity into this limit, I'm going to get e to the negative infinity, which is going to be 0. If I put in 0, I'm going to get e to the 0, which is 1. So this is going to actually be integral from 0 to pi over 2 of 1/2 d theta, which is a funny way of writing pi over 4.
Is it negative 1/2?
It's positive 1/2 because of the fundamental theorem. It'd be plus this one minus that one.
Oh, right.
Yeah. And so do you remember what's on the left side of this equal sign?
I swear over 4.
Good. I squared over 4, thank you. So we get that I, or the integral from negative infinity to infinity of e to the negative x squared dx is equal to square root of pi.
Duh.
Duh, exactly. Like totally obvious, right?
So where'd you get the pi over 2 on the second integral?
Here or
Yeah,
here?
at the top one.
Because our region in the first quadrant is starting at theta equals 0 and going all the way
Oh,
to
it's going
vertical.
to the vertical y. Oh, okay.
Yep, exactly. Exactly. All right, I want to pull this stuff back together and conclude. So the derivation is here in the notes if you want to work through it more slowly. But after working through this example, it is clear that this formula is not obvious. It's not obvious to me. It's not obvious to the author that wrote it the first time. And so the conclusion seems to be that Lord Kelvin was showing off and he was putting down his students and being mean about it all at the same time. So please do not think that I believe you should just know that like you know 2 times 2 is 4. But this particular function is really important. This distribution right here, and you can see right in the middle of it, there's your e to the negative x squared. This thing is called the Gaussian distribution, and it's tied to the normal distribution curve or the famous bell curve. It's used all over the place to try to describe populations. And so you say, why are some people really tall and some people really vertically challenged, but most people are sort of right in the middle? Well, that distribution of heights is described by the Gaussian distribution, or this curve. Tossing coins, rolling die, distribution of brain power, shoe size, birth weights, even your grades are roughly speaking distributed according to this. And so as we look towards things like COVID, we could ask, what is some of the math that we could do? What are some of the distributions that are impacting this COVID crisis? We might not be using the normal distribution curve, but these ideas from probability, these ideas from calculus very much do have bearing on the world in which we live. And so I wanted to do this particular equation because it's interesting, because it has a good anecdote, but also because I think it's a good segue question to help you start thinking about how we could use the math that you're learning to understand the crazy world in which we all find ourselves. So just wrapping up a summary, may your blessings be many and your challenges relegated to the tails of the bell curve, those outer fringes where there's not much area under the curve. So have a wonderful day, everyone. I'm happy to hang on the line if you have any questions, but that's all there is for today. And sorry for going a few minutes long. Take care, and I'll see you all tomorrow.
Thanks, Dusty.
Questions?
Yeah, so I had a quick question about the My Labs.
Go ahead.
So after the 14 days is, because I just got access to it just now, right? So by the end of the 14 days, we're still going to pay for it, right?
No, it should be
Right.
100% free for you. But that reminds me,
Wait, okay, so
don't spend any money. I think I have an email telling me what to do, but I have to go back and look at it. I will jot
Okay.
myself a note.
so that's going to be from your side then, right?
Yeah,
Okay.
you don't have to do anything. Just my lab codes. I'm not sure. It's possible that I'll just have to give you a code and you'll have to enter it in. I don't know how that works.
Okay.
Good question. I jotted myself a note. I will take a look at that and
Right.
make sure that that's addressed.